have with us today Dr. Allessandro Pinto from United Technologies Research Center. United Technologies has a very long history of collaboration with this institute since the very beginning, 1985, when John Cassidy was the director of DRC, and there have been several projects with DRC. Even currently, we have one with Professor Pitts in the design of optimization algorithms for helicopters. So, Dr. Pinto is a researcher in the systems department at the United Technologies Research Center, and he is lucky enough to work at Berkeley, California, for that center. So his research interests are in the area of computer-aided design of cyber-physical systems, with particular emphasis on autonomous systems. He received his PhD from UC Berkeley in 2008, and before that he received his laureate degree from Rome, Italy. And from 1999 to 2001, he was a consultant at Ericsson Labs in Italy, working on the design of systems on chips and wireless access networks. Today, he is going to talk to us on the development of tools for systems design, a topic of great interest to all of you here. So, welcome, and thank you for coming.
It was very difficult to put together the material for this talk, by the way, because in the past couple of years we worked on several programs on system design, and so summarizing everything, like 2 years of development in an hour was very difficult. So I will definitely go in depth at the beginning, on the first part of the talk, and I may go fast on the last part, which is a more technical set of tools we developed for dynamical systems. I already introduced the UTC to a restricted group of people, but what UTC really is a conglomerate of different business units. There are two segments. One is the commercial segment, and the other one is the aerospace segment. We do all sorts of products. So in the building area, the commercial segment, we have carrier air conditioning systems, from small to large installations, OTC elevators for vertical transportation, UTC fire and security that takes care of fire detection and suppression, and also as a security system, of course, for access control. UT power is also a growing area. We have wind generation, fuel cells, and then the aerospace is the one I feel closest to, so I'll comment more on this. Pratt & Whitney is one business unit that builds jet engines, and Hamilton Sandstrand several products, but of course electric power systems and air management systems are the one that are most known. And then we have the Sikorsky business units that builds helicopters. So Sikorsky is really builds the entire helicopter from start to finish. The research center helps all of these business units. They typically come to the research center with problems, system engineering problems, and they ask us to help. There are several sites, kind of distributed globally. There is a small site in California where I work. Then there is the main site is in East Hartford, Connecticut. And there is one site in Europe, in Cork, Ireland, and that is growing, by the way. And there is one in Shanghai, China. That's actually has been established 10 years ago already. And there are several researchers now, I think about 50%, I don't remember the number exactly. And one other important thing is that we are constantly, I would say, hiring. So if you're interested in knowing more about the company, you can just send me an email. So let me talk a bit about complexity in aerospace systems and why I got so interested in it. Complexity comes from several factors: heterogeneity, coupling, and safety requirements. So we'll discuss a bit about them. But heterogeneity is actually manifests itself in many different forms. It's not only because systems are of different natures that are put together, but there is a whole other aspect to it, which is the heterogeneity of the skills that you have in a company. So it's difficult to find a system, well, let's say an engineer that can really master every single domain. Of course, with time you learn about everything, but thermal management somehow is a domain where few people have expertise, and then there's electric power system is another one. And just to frame the discussion about complexity, this is a very small, a very high-level rendition of what an aircraft may look like in terms of the subsystems. So you have an engine, The engine is the one really that transforms the chemical energy in fuel into any other source of energy. But typically, mechanical energy that is transformed into electrical and so on. So there is all sort of energy and mass flow that goes on in this diagram. The fuel is burning here, and that is used to spin the big fan that you have in the front, and also moves the gearbox. The gearbox moves generators to provide power for the electric power system, and moves also mechanical equipment like fuel pumps. The fuel pump pumps fuel that is used for many different things. They're used to move actuators as well as to cool down things. So there is also a coupling because you need to cool down the electrical equipment using perhaps an environmental control system that dumps it into the fuel that is used to somehow spin the engine that is powering the electric power system. And if we move to even more electric aircraft, where basically we're trying to use the electric power to even move this part and avoid the engine to move it, then well, directly from the shaft, then you start seeing that there is really a feedback loop between them that can cause all sorts of problems. Also, so coupling is the other issue. And the last part is safety requirements. So this system must be somehow safe, and therefore there is all sorts of redundancy in this system. If you look at this diagram, for example, you can see 3 generators here rather than 1. In many systems you have 2 engines rather than 1. And redundancy must be managed. So that brings up all sorts of other complexity problems. So I think I was lucky because being in this company was able to see the real system. And the real system is of course incredibly large. And I was also lucky in another context for Sikorsky to see actually the assembly line, see how complex that machine can be. Seeing it so big and so agile really makes you think that there are big challenges that engineers as of now have been able to solve, but that for future products can be a problem. So cost overruns are under the eyes of everybody with the JSF program, for example. And that was one of the motivations that pushed DARPA to establish a program, the Adaptive Vehicle Make program, where we actually participated as performers. This is a slide I took from Paul Remen, who's the program manager there. And what this diagram shows is somehow a rough notion of complexity. Is already a different talk to talk about what complexity means. But roughly, what the diagram is trying to say is that even if complexity of products have increased in all different, let's say, businesses, let there be the semiconductor industry or the automotive industry, the development effort has been somehow maintained at the same level for these 2 industries. So one big difference is the aerospace industry, where the development effort increased exponentially. So one objective of this program was to reduce it by 5x. That was the overall goal. That is the overall goal. What has been noticed is that both in the silicon industry and the automotive industry, at some point in time, there has been a radical change in the way we design things. So the LSL design saw really the introduction of tools, and the automotive industry the same. That didn't happen for the aerospace industry that is still using the old military standards. So the objective is to change the way in which things are done. As performers, we joined this program, and we proposed one system engineering effort to just develop a comprehensive system design toolsuit. And what I'm going to talk about today is more the contract-based specification. And the second part was to develop verification tools for systems with dynamics that are potentially distributed. So these are really hybrid systems, if you will, but where also uncertainty plays a role, meaning that many of the parameters of the systems can be uncertain and characterized by probability distribution, for example. And a full report is available on my website, and I will touch on just a few of the findings. So this is what we proposed. Let's say what we noticed, This is what we conceptualized as important things to research on. So if you look at the, and by the way, this is a slide I took from Brian Murray, who is the group leader in the embedded system group, and I work for him. So in this, on the left, what you see is really the standard design process. What we see about it is this time pyramid, if you will, or development effort pyramid, where most of the time is spent here, at the system validation level. You do your conceptual design, partition the system maybe with drawings or with the specification written indoors. You ship them to your subsystem developers. Eventually, you put the system together and fly, see what happens. Most of the time it doesn't work, and you go through long redesign cycles. And then system validation again. So most of the time is spent here, very little up there. And the proposal was to reverse this pyramid, if you will, and spend most of your time in a virtual engineering environment where you can do your trade-offs and you can prove property to the system. And use the system validation only as confirmation that everything is fine and it works. Don't use it as the primary way of looking at the system trade-offs, so verifying that the system works. So to do that, what you need are several different things. First of all, you cannot design the entire system just looking at the very details of everything. And so what you need is to divide your design process into abstraction layers, where you start doing system-level trade-offs and then refining your subsystems. And of course, you need a virtual engineering environment. So you need languages that are able to capture all the different aspects of the design. And when you look at that specific aspect of the problem, what is the right language to use or the right set of constructs to use, then you find pretty much that the content-based aspect or specification of the system is what you really need. And I'm going to motivate this with some simple example that you may find useful. A lot of other things that we consider during this project is the notion of when your product is really optimal for the system you're trying to design. So you need to start defining all sorts of different metrics, including complexity, of course, but adaptability is another one. Maybe 5 years from now, the government comes back with a whole set of new missions. Can my system adapt quickly to this new set of requirements? But performance, first-time cost, maintenance cost, there are all sorts of different metrics you can define. So we couldn't really build an entire system. We had models though, and looking at the models, a professor from MIT, Olivier Beck, was able to put together a model of the system design process and actually prove, at least on paper, that this new way of designing system could actually lead to a 5x improvement or a reduction in development. So why is the language so important? Well, first of all, we talked about the virtual engineering environment, and therefore, we need to have models, right, rather than actual real pieces of hardware. And this is not really code. Right? If you only have code, you don't go much far. What you really need is models in some sort of formal language. However, you need to deal with legacy models. How do you bring them in? So we talked today about the notion of interfaces, which are critical. And that's why eventually we relied on contra-based design, which is a nice way to capture these interfaces. What are the modeling requirements, if you think about it? So we need to be able to do integration, and we need to be able to have a way of going towards independent implementability. Because you have several different subcontractors, what you want to do is spec out your system, deliver the specs to your subcontractors, and if they design according to specs, you don't want to have surprises when you bring these pieces back together. You need to have multiple related views. It comes back to the fact that we have experts that can do very detailed analysis of power quality in the system and tell you all the harmonics and stuff. And we have other experts that are able to tell you exactly what's the heat dissipation on every single box. These views must be related to each other. But you need to be able also to do this analysis in a separate way. You need to have multiple abstraction levels, again, because problems are complex, and you cannot just work with very detailed models and that's it. So at this point, these abstraction levels are many, but they are related. So you need to have a way of formally defining when when one model is an abstraction of another model. So now let's go through a small, simple quiz. I have a resistor, and there are two variables, the voltage and the current. And I built a model maybe in Simulink, and I decided the voltage is the controlling variable, so that's the model. Okay? So the simple question I have for you is this the right model of an ideal resistive load? Is it? How many say yes? It's an ideal resistive load. Yes, is the right model. It's an ideal resistive load. Is this the right model of a load? Not at all.
It's not even the first one, because what if maybe non-linear?
It's an ideal resistive load.
Whatever.
So it is for
Yeah,
that.
when you write V equals Ri,
Yeah.
you violate my basic electromagnetic.
Yeah, I'm just saying, it is an ideal resistive load. This is a good model. Yeah. But if I say, is this the right model of a load? The right answer should be no. So one thing that may happen is that the frequency of the input voltage is very, very high. So, okay, then is this the right? Is this a better model? Maybe not.
Maybe.
Is this a better model? Maybe not. The actual, the reality is that when you develop a model, you need to say when that model is valid. You cannot just take it and ship it and say, so go off and use it, because you need to define when is the model a good model. So a linear model may be good within some bounds of the input voltage, for example, which is a perfectly fine model, and people can use it as long as they know about it. So can you use Simulink to define the validity bounds of the model? Of course, you can always do it. You can hack it somehow. But it's not really the right way. So that's why we started looking at contract-based design as a tool to do this. So here is a mathematical definition. I don't even want to go into the details. I may not even have time. But here is the concept. If you have a component, you have some variables which you judge uncontrollable because they are set by the environment in which you operate. And there are some variables, x, which are actually considered controllable. So those are the variables that the component decides based on the uncontrollable ones. So an example was the resistor. If it's controlled using voltage, then voltage is uncontrollable and the current is the controllable. So each variable has its own domain, and the domain of the set of variables is the cross product. Let's not get into technicalities. But a contract is a tuple where V is the set of variables, and then you have two other sets. You have the assumptions and the guarantees. So the assumption, here is what the assumption is a limitation on the environment, saying I am going to behave according to the guarantees, which is a relation between input and outputs, if the assumptions are met. So this is the contract. And once you define this contract, you can define all sorts of other stuff. So if I have a model, is the model actually satisfying the contract? You can mathematically say that. You can compose contracts. If I have two contracts, you can actually compose them and derive another contract, which is basically putting together system to subsystems. You can do conjunction, and this comes back to different views of the same system. If I have an electric view and a thermal view, I can use the conjunction operation to come up with a single contract that brings them both together. So it seems to be a nice environment. The other interesting property is, the other thing you can define is the refinement operation. If I have a contract and I have another contract, when can I say that these two are related by a refinement relation? So, well, you can say that because refinement is really a way of capturing when a component can be substituted to another component. So if it's more refined, then which in this context means it can accept more environment and it can provide better guarantees, then I can substitute that. So all these notions are all the ones that we need. Notice though that this is a very denotational definition. It's really sets, containments, so on and so forth. And the devil is in the detail. When you go off and implement a tool using these operators, then depending on how you represent the set, then implementing these operations may be a big challenge. So a high-level view, what can we do? We can have a component, have several views associated with it. Doesn't matter, we can do conjunction to write one contract. We may have a system with several components. We can compose them and generate one contract, which is going to be checked against the specification of a system, for example. Okay, the system works. I can take C4 as a spec of another system, send it to a subcontractor and ask, please implement the system the way you want, using maybe 2 blocks, as long as my contract C4 is satisfied. And that's the refinement problem. So it's a nice framework. It's really for us, it's what we are embracing. Now, just by the general definition, you can prove some rules, inference rules. For example, this is the independent implementability. If I have 2 contracts and I have 2 models that implement them, the composition of the contracts, the composition of the models would satisfy the composition of the contracts. And other rules. But again, as I said, when you go and implement these languages, these operators have to be implemented eventually, if you will, with an algorithm. And so you need to be careful what you pick as specification language. So how do you capture sets? The way of capturing set, for example, is set of constraints. Constraints define a set. If you are talking about behavior, a linear temporal logic formula captures a set of possible behaviors. So it depends on how you specify the sets. These operations will change their nature, their implementation. So as a simple example, we can look at this a generator and a load. I like this example because it's easy, can be understood. Let's take a generator, and I define the variables this way. So the uncontrollable variables are its input current. That's the requirement from the loads. And the generator cannot control that. The loads will require current. The generator provides the current. And I also include 2 parameters as set by the environment. In this case, it's the human that is designing the system that is setting these parameters. One is the internal impedance. The other one is the nominal voltage. And then the output voltage is the variable that the generator can actually control. It can decide. And the assumption is simple. It says if the power requirement is less than a maximum power requirement, then I can guarantee that the output voltage is the nominal voltage minus the voltage drop on the internal resistor. So the load is somehow similar, and it's actually saying, look, if my input voltage is within 10% of the nominal voltage that I really need, then I behave as a resistive load. That's the assumption. So now you can take this model, you can instantiate them, and to connect, you can do several things. One standard way is renaming. So I'm going to rename these variables so that now they have the same name and therefore are connected. And you can now compose them. And once you compose these 2, what you get is the full contract. So you take the conjunction of the guarantees, and then you need to do some more tricks for the assumptions. But the key point is that this is another contract where these are 2 inputs now, and I have an assumption on them, and these are the guarantees that are only visible actually internally. So anyway, simple exercise, but the other quiz that I have is the following. Can we instantiate more than one load here? The answer is no. We cannot, because if I instantiate another load and I call that the output current again I in, I don't actually know anymore. I mean, the meaning is that I would just put another equation here and the system would have no solution. What I really want to say when I instantiate another load is that the 2 currents would sum up to give the total current requirement. So I now suddenly have to add a new component, which is an adder, or something that operates on currents and computes the sum, but I don't really want to do that. So anyway, this admits that there is something missing in this framework. The second is, can we instantiate an unconnected component? Yeah, I can instantiate a load. Although, if I have a product family, like I provide electric power system, and here is my product family, and go ahead and put it on your aircraft, and there is an unconnected load. So, first of all, it may be a mistake or an error. But the second, if it's not an error, it's done on purpose, then of course the airframer would ask me, why do I need to carry this extra weight that is not connected to anything? So we need to be able to express what are the desirable properties that any instance of a platform, of a product family, cannot violate. This is another thing that we need to be able to specify, and it's not in this framework yet. So we need two things. We need a way to define an algebra that can put together these quantities somehow, that tells us what are the rules of the world. So if I have two loads connected to the same node, their current will sum up, for example. Something that Modelica would do, for example. And we also need a way of defining other types of rules that tells us when an architecture is valid. These are rules that could be violated. The whole architecture will still work, but it's not desirable. And add this to the same, no, they are different. So that's why our effort was to develop a language to describe product families or platforms, so sets of possible architectures. And what we did to allow the specification of those two previous rules, we used first order logic extended with some background theories. Specifically, I'll talk about this a bit more. And this gives us the ability to model platforms, a set of products. Then what we did, we went and we said, okay, now we have to be able to implement all this. So we developed tools to do it. And I'll show a demo right after this. So what are the limitations? So notice that these limitations come from two things. First of all, we want to limit the complexity of the analysis tools, and then we want to use tools that are available. So we decided to go for steady state. So there is no notion of time, but however, you can model modes of operations. So we know that, for example, an aircraft can be in taxi mode, can be in climb mode, cruise mode, descending mode, and eventually landing mode, for example. So in each of this mode, you can model a set of equations without notion of time that represent the steady state operation of the aircraft in that mode. That is important because that's how you evaluate losses. Losses really matter in steady state, not losses in transit are minimum, we don't care about it. So we limit that to steady state because when you introduce time, then it's very hard. The verification question becomes very hard. The second one is to limit the type of constraints to arithmetic expressions. The reason for doing that is because we have very efficient solvers that can deal with arithmetic expressions. And if you start allowing all sorts of other type of expressions, then the solutions become unique and all sorts of problems. So eventually, this is what we had to develop. It's very small, so you cannot read everything. But this is the actual meta model that we use for tiny CSL, this language. So you can develop, you can capture platforms up there, and they have two sides. One is the library of components to describe all the components you have in your library. Just imagine a big shelf with an engine, an electric power system, whatever you want. Those are all the components. Components can have different views, electric, mechanic, thermal. And each view has a set of variables, the controllable and uncontrollable ones. And they have two sections, assumption and guarantees. And these are constraints. Constraints, you put some syntactic sugar. They can be simple constraints, all sorts of logic with predicates that can be relations among expressions. And if-then else type constraints, just to simplify the specification process. On the other side, we have rules, and rules are a bit more general. Remember, we are modeling platforms. So we don't know, for example, how many generators are going to be in there. So we need to be able to use quantifiers. Indeed, when you specify a rule, that's always quantified because you don't know what's in there. So you need to use usual quantifiers for all that exists. And that's really first order logic that we are using. And that's the meaning of these constraints. So we can have quantified constraints within a rule. We can do a bit more. if you have to express things like the sum of all the currents of all the loads must be less than or equal to a certain quantity, you need to do two things. You need to define a set of objects, which is the set of all loads, and then an operator on that set, which is the sum of the currents. So we allow the specification of set quantities, meaning grouping objects into sets, and we allow the specification of operators. So we have in this case two operators because the one that is easy to implement. One is the sum, one is the cardinality of a set.
So the line is written on what?
This is what's called incur modeling infrastructure. So incur is a very minimal set of models. Modeling, it's a meta model. It's a very minimal set of modeling artifacts. And on top of that, we develop our own meta model, which is this one. And this is really capture all the possible programs, if you will, you can write. Once you develop this way, then you can do all sorts of model transformations to get to verification code. I'll show you an example. Actually, let's go ahead. So I need to switch workspace. Let's go over quickly some instances that we got ready for you. So let's see a platform. Okay, so you define a platform. In this case, is a electric power system platform. It's a very simple one. So platforms can have, as we said, two things: libraries and rules. So there is a library of components, and this library contains components, so in particular a generator and a load component. These are component types. And the component has an electrical view. So if we expand, I have variables, and in this case I have a nominal voltage for the generator, the input impedance, resistance actually, and the input current, and then the output voltage. And then define assumptions. So in this case, I define a maximum power of 70 kilowatts, and I'm also saying that whoever is setting the nominal voltage, maximum that he can set is 270 volt. That means that I have a certain number of generators, but the maximum voltage I have on my shelf is 270. So whoever system engineer is configuring the platform cannot ask for a generator whose nominal voltage is higher than that. And then the guarantee is what you've seen as well before. So output voltage is the nominal minus the internal voltage drop. Component, a bit more complex. I define two types of loads. One is at 270 volt, one is 115. I can put assumptions. This is a complex if-then else statement, and it says if the load is 270 volts, then I can accept an input voltage which is 10% within 270. If the load is 115, then it has to be within 5%. And in that case, the load is going to behave as a linear resistor. So when it comes to rules, they're more complicated. So we can use, again, to start the logic operators to, for example, state the same. For all G, any component G, which is a generator, an instance of a generator. Now, this is a nested operator. There exists L, the component L, which is a load, so that the generator and the load are connected. The connected predicate is a predicate, is meaning a function that returns a Boolean. And the assumption is that you can define it on components, okay? You can define whether the predicate is true. If you don't define it, then it's false. Okay? It's called, first of the logic, this is called, I forget it, I'll tell you. Anyway. The same for loads. For all loads, there must be a generator which is connected to the load. Then a voltage assignment for all generator, for all load that are connected to it, the for all load, either the node is not connected to that generator, or if it's connected, the output voltage of the generator is equal to the input voltage of the load. And then the last one is the current balance we just talked about. So in this case, this is the set quantity I talked about. I'm going to look for all the loads connected to this generator. I'm going to take the sum of that current, and this defines a function from generators to total current. And then I'm going to say that for all generator, their input current is equal to this total current. This is a way, using first-order logic, to capture the algebra of all the quantities of the rules of the world, let's put it this way. Whereas these other two rules, like generators must be connected and loads must be connected, these are more validity rules, meaning that it's a desirable property that your instance must have. Then you can create instances, in this case, very simple instance. The instance is the following. I'm going to instantiate two loads and one generator. I'm going to set up the parameters, load type, internal impedances, and then I'm going to define these two predicates, meaning the generator is connected to the load 1 and the generator is connected to load 2. Okay, so now I have an instance and I have my platform definition, and I want to check if the instance is an actual instance of the definition. So in this tool, you just right click. Just right click. There's a set of tools we developed. One of them is to verify the instance. And the verification will tell you if there are rules that are violated. In this case, actually, the voltage bound on the loads are not satisfied. So those rules are violated. The way we do this is we take this model and we translate that into the input for a satisfiability modulo theory tool. So we're going to put all the rules of the world, all the rules of the models in terms of assertion, and then we are going to query the tool for all those properties we want to be satisfied. So you can read more about this tool. You cannot go into the details of how this translation is operated, but that's the concept. Now, let's go back to this. We talked about these models that are steady state, so you may ask about dynamics. Okay? So there are two ways of abstracting. So one is abstracting in the timescale domain. So you ignore, for example, fast transients, and you can do that all the way up to steady state model. An example of this is logic design. We use a steady state abstraction. So we assume that our circuit is always either in the 0 state or in the 1 state. It's the steady state. Actually, there are waveforms there, so we don't do that. That's one axis. And then the other one is scope, when I basically represent big chunks of components into one component and I define the interfaces. So we now basically looked at all systems that lie on this axis here. When we use actually models, we mix all this. It's a fluid level of abstraction levels somehow. We typically go this way. We don't move just around here. Actually, this is the traditional process. We don't only move over the steady state axis. So how do we do that transition? Well, let me tell you quickly what that means. So we've considered this case where we have different phases. And what typically people do is check for the steady state properties in all of these states. It's called quasi-static regime. In each state, what you have is really a system of equations. Okay. Then, when you want to move to dynamics, you start including transitions among these states. What are the transitions that are valid, and under which switching conditions they happen. And in each of the states, you have a system of differential equations that define the dynamics in that state. So this is called also a hybrid system. On top of that, you can add uncertainty, meaning that, for example, during a mission, you don't know if you're going to climb up, go down, and cruise. You don't know exactly how the state is switching. So you may include a probability because you don't know about the details of the maneuvers. Also, within each state, you may not know exactly how the system will evolve. There are sort of parameters. I don't know, weather, temperature, whatever you want to put in. So the problem that we had to look at, that we wanted to look at, is how do you analyze the system on the left. Okay. So we then, first of all, fixed the mathematical framework, and we picked discrete time stochastic hybrid systems. In these systems, you have modes of operations that you've seen before. You have continuous state spaces within each mode. These are continuous variables. And you have transitions between them. But what we consider are those systems where the dynamics within each mode is actually a stochastic map. So it depends on variables that have a probability distribution. And also we looked at jumps between different modes that are also stochastic. So instead of having a jump with a precise condition, the jump will tell you what's the probability of going from one mode to the other. Finally, when you jump, you go from one mode to the other mode, you have a chance of resetting your state variables, meaning changing the variable instantaneously, not in a deterministic way again, but according to a stochastic map. Meaning that if I start from taxi mode, I start climbing or taking off, I may end up in different states of the fuel level, for example, just to model that uncertainty. That's just one.
And this is synchronous, right?
This is synchronous, the discrete time stochastic hybrid system. It's a synchronous. So we announced this with inputs and outputs and all sorts of other features which I don't have time to go through. So an example is a stochastic bouncing ball. I'll give you a more concrete example later, but it's a very simple example. So in this discrete time view of the world, I have a bouncing ball, and the actual acceleration is uncertain. Okay? Also, the restitution factor is uncertain. Whenever the ball bounces, the reset, instead of inverting the velocity with a deterministic restitution factor, that is also uncertain. So now the question could be, for example, what's the probability that that the ball will jump higher than a certain height, maybe higher than the height it started from? Because the acceleration is uncertain, just imagine that there is wind all over. That could be one question. So we developed a set of tools, and I'm going to switch workspace again. We developed a whole set of tools, actually a complete verification tool suite for doing simulation and reachability analysis for these type of systems, and also statistical verification. All these concepts are related but not different. This is all implemented actually in C++ for efficiency reasons. This tool must be very efficient, it needs to handle lots of states. So we developed this type of tool. We are going to have basically a core library that provides simulation capabilities, provides the meta model, all implemented again in C++, and all the other algorithms. And then there are models that we develop. Let's look at the bouncing model, bouncing ball example. You can model the bouncing ball by defining its states. In this case, y, which is the altitude, and v, which is the velocity. You define the modes of operation. And in each mode, you're going to define the stochastic maps, which is exactly the equations you have seen before. You're going to define also transitions, when it transitions in modes. In this case, this transition is the event of jumping back from when it hits the ground. Once you develop all these models, you can run several things. You can run simulation. So I did run it for you, so I can just load the results, although my MATLAB session has expired. So let's go to the simulation first. Actually, I can do this.
So the simulation is done by linking this to simulate or what?
No, actually we have the simulator implemented, all in our library.
Only your own?
Yeah, because there are a lot of small things to check. So, but simulation trace, for example. Notice that, again, the restitution factor is completely random. So sometimes it bounces higher, sometimes it bounces lower, the acceleration is higher. So that's why it's not a very nice bouncing ball. There's a lot of noise here. But what you can do, I think, the majority of the effort simulation is a very trivial thing to do, is in actually computing the full probability distribution and how it evolves over time. So this is the bouncing ball, this is the velocity axis, this is the position axis, and this is the initial probability distribution. Okay? So I'm assuming that it's roughly at 2 meters high and the velocity is 0, but there is some uncertainty around it. Okay? So that's why its probability distribution is not a point. And then as we start evolving time, this probability mass starts moving. And of course has to spread out. And now here it starts jumping back. So for all those events where the actual, this is the probability distribution, for all those states that are here, they start bouncing back. So that probability mass is now shifted to the next mode. And then you can go on and simulate the full probability distribution. You can do all sorts of other analysis, but I wanted to get to some conclusion before the time goes by. The main idea here is not too difficult. Let's say that you have a probability distribution over a state space. Let's call it mu. You want to understand how this probability distribution mu at time k translates into a probability distribution mu at time k plus 1. So the condition that needs to be satisfied is the following. For any set A, the total probability mass in A at the next time step needs to be equal to the total probability mass if you do a back projection of A according to your map. If it's a stochastic map, then there is an expectation you need to take. But what you're really doing is you're moving forward these probability masses. And to do this, you need to discretize the state space, which is part of the problem. So for each mode, you have a continuous state space which you have to discretize. There are techniques, but at the end of the day, if you cannot make assumption on the dynamics, meaning the stochastic map, you must discretize. This is the and of course, if the discretization is very small, if your cells are very small in your state space, then these algorithms becomes very complex. So what we realized, so we did apply this to the case of a thermal management system, where we have a fuel tank with an initial mass and temperature. There is a pump that pushes fuel through the circuit, the fuel circuit, and there is heat that is dumped into the fuel, and then part of it is going to be burning the engine, part of the fuel will go back to the tank, going through a heat sink that is typically cooled down using external ram air. So the question would be, if I fly the entire mission, what's the probability that by the end of the mission, the temperature in the fuel tank is too high? So then before you need to set up a mission. That's a very, let's say, nice and simple mission. We have to set up parameters like climb rate and all these other things. And we model this again as a hybrid automaton that goes through different states. Transitions are stochastic. And eventually, we were able to compute this in roughly half an hour with a lot of optimizations on the model, because otherwise it's difficult to run.
How many modes?
Say that again?
How many modes?
There were, I think, 7 modes or 8 modes. But the problem we discovered, well, we realized actually, everybody realized, so it's not a discovery. So the problem is not the number of modes, but it's the number of continuous variables, because the complexity of this algorithm goes exponentially with that number, because each variable has to be discretized. And indeed, that if you look at the actual limitation in practice, without claims that are untrue, but this is actually pretty much close to reality, let's say. The limit is to 10 million reachable states of this discrete state. So if you go and look at the type of number of continuous variables, of course this depends a lot on the dynamics of the system, but it's roughly 6 to 7 continuous variables. That's the limit. It's somehow a limit. Nobody has been able to break so far, unless the system, again, has a very nice structure, but there are no such systems. And that means 3 for components. So this is the limitation. We cannot go further than that. Yeah, we're good. We can handle 10 million reachable states, but it's not enough. So that again, the way we try to tackle this is 2 ways. First of all, using contra-based design. It's true that you can handle only 3 components, but if you can verify a property at this level, then the question is, can you take whatever you computed for a subsystem and just verify, zoom in that subsystem and verify that the property is maintained by the way that system is constructed? It turns out when you try to do this for probabilistic systems, the answer is it is very hard to do it exactly because it's not easy to compose and check refinement among probabilistic contracts. So what we proposed is an approximate way of checking refinement. Again, it's approximate, and therefore the solution cannot be proved. So we did this again for the same example where we now refine the heat load into the entire oil circuit that cools down the engine. And we started looking at approximate refinement. So basically computing a distance from the original system to the actual refined system. And you can do this. So the idea is to stimulate with the same distributions, probability distributions, the 2 models, an abstract models and a refined model, and compute this metric, which is really a distance of probability distributions. Somehow you can do it, but again, I don't think this is a way to go. It doesn't scale. So I would like to conclude the talk saying that what we instead have done is to go towards a synthesis approach. So rather than saying, I have a property I want to verify, so I take my system and I check the property. It would be much better if we had a process to say, I want to have a system that satisfies this property. How should the system be designed? So that's more a synthesis question. So one example, for example, still for this system is to say, let's say I have my thermal management system and I can control the speed of the fuel by looking at the temperature, and I can control also the heat sink by looking at the temperature. So now the problem is, I want the temperature inside the fuel tank to be a certain level with certain probability. What should the controller be? What should the controller of the system be so that that property is satisfied? So that I don't have to check. Right? Of course, this question may not be easy, so it depends on the way in which the controllers are written and leveled. But we do have a way of doing this. So we use, sorry I have to skip these technicalities, but the idea is that we use the stochastic optimization. We fix the control policies and we leave them parameterized. And then we use stochastic optimization to enforce that the probability of having the fuel temperature exceeding a certain threshold be less than a certain value. And then we synthesize the controller, we flew the same mission, and let me check for the temperature. This was the temperature. We have 2 types of temperature. One is in the tank, one is at the combustor, just at the end, when it enters the engine. And you have constraints on both. The optimization was able to, first of all, keep this temperature always between 280 and 281, 22. And then keep this temperature within a tight bound around 333 actually. But definitely no more than 340. That was the hard constraint. So at this point we don't need to verify because the system through the optimization already satisfies the problem. So if we can do by construction the system so that we don't have to check, that's a better approach. And by the way, has been done in many other cases. So there are architectures that are safe, you don't need to prove anything about them, for example. If you use a triple redundancy module, you know that you have a certain reliability you don't have to do. Well, I want to go to some conclusions and say, okay, the big motivation was complexity. Pick your definition of it. There are many. But that's the driver for virtual engineering. You cannot get to prototyping for a complex system. And an important part of it is languages and tools that allow virtual engineering. So we focused on content-based design, and we developed our own tiny system language and verification tools around it. And then once we did this for steady states regime, then we moved to dynamics and uncertainty. And here we developed method for analysis, but we noticed that they do not scale. No matter what you do, the problem is too hard. But we also looked at some synthesis approaches that are able to force this problem to the construction, and they are very much promising. So we are going to pursue this. Well, thank you very much. It was long. Sorry. Thank you.
Do we have time for some questions?
Yeah, it's time for one.
Yeah, go ahead.
Where do you get the probabilities?
There are many ways to get probabilities. So if you talk about weather, for example, then that's not much of a problem, right? You have large databases to create the statistics. If you look about, if you want to capture, I don't know, component failure, you go the spec tells you what's the probability of failure. If you are looking for probabilities of, I don't know, probability that probability oriented that you definitely don't know or has not been characterized well, then probability is not the right way to know it, in my opinion. But non-determinism is the right way to know it. You just don't know if that event is going to happen or not. You cannot associate a number to it. Just include that as a non-deterministic event that can or cannot happen. At that point, you need to verify the system in both situations. But by the way, one thing is, one of the methods that seems promising is one based on simulation. So statistical methods to do stochastic verification, which, by the way, does not work for non-deterministic systems. And that's a big problem for it. You may look and I can give you reference about this. But definitely, in the case where you don't have those probabilities, you just don't know it. You just consider it non-deterministic. That's the only way to go.
Any questions?
I think it relates to the same question, but doing sensitivity analysis on your assumptions, like on the choice of the probability of the model, and varying the characteristics to see what the performance, whether it still stays, and how far it strays from your desired.
Yeah, there are methods to do that as well. You can, for example, you can look at the sensitivity of the fuel, in this case, temperature, to weather conditions. Right? Is it sensitive or not? As out it is. But for other cases, like, what's the sensitivity to taxi time? Right? These are the certain parameters. And then you can say, okay, if it's not too sensitive, I don't care, and I really neglect that aspect of the system. We collaborated with UCSB, actually with a company spin-off. It's called IMDyne, and they have a comprehensive tool that can deal with thousands of uncertain parameters and give you all the sensitivities so that you really focus on the 5 top most parameters that really influence the performance of the system. Definitely, it's the first thing to do. You don't want to carry over all these probabilities if you don't need them. If they are very sensitive, you better get them right, otherwise the analysis doesn't work.
Any other questions? I have two. Oh, sorry. Go ahead.
What about energy? I mean, when you show this example of the ball bouncing higher, I'm like, when did this energy come from? There's got to be, there's conservation of energy, and it's a physical system, right?
Yes, it is.
Yeah. So in this framework, is there any notion including energy balances?
So when we talked about the contract specification language, one of the things we wanted to make sure it's possible to capture is this algebra or quantities.
Right.
So for example, you know that current adds up in a node.
Just
The
consider
same
quantity,
thing,
but,
yeah, same thing would be the energy conservation of energy.
Should be part of the world, the rules of the world.
Yeah, the rules of
Right.
the world will be, but the challenge, of course, is to write the model, right? So it's not easy. By the way, even with modelica models, one I think challenge I always find is that if you build a complex system, although yes, it's you may claim if all the modules are right, the system is right, but it's very difficult to debug. If it doesn't work, maybe you forgot one of the fundamental rules of physics somewhere. So it is indeed difficult to build the right models. That's definitely true. But we have the provision to do this.
Any questions? I have two questions. Let's ask the more difficult one. If you're going to do synthesis approach, you need to answer questions like this. I have specified a component that I may need according to certain metrics and other things that I'm missing, and I run this, right? Suppose it comes back and says, I don't have anything. You need some sensitivity analysis to tell you how to modify to have a more likely yes answer. Where are we in that process? That's like more what he was asking you, right? I mean, try to find the impact of the sensitivity rather than the traditional sensitivity of a given parameterized model. That we can do,
Lots of tools for sensitivity analysis for sure.
but not in this way.
But we haven't linked it to this type of models yet.
So how far away from the feasible domain?
Yeah, no, we haven't. What we did, in that respect, we did something slightly, maybe different, but maybe pertinent, right? We looked at adaptability metrics. So we defined them not as the ability of your system to adapt to some different conditions in the environment, rather to adapt to completely different specs. So it may be fine to change the system a little bit, as long as you don't change it too much, to maybe satisfy other requirements that may come later after the system is built. So we associate then changing costs, which is the notion of distance between two architectures. So how far is this architecture from this other one, which has these other capabilities? But we studied that on the temporal networks. So how costly it would be to change my product over time to adapt to more and more performance requirements. But we haven't used it for example.
The other question I had is sometimes, when you have to deal with uncertainty, sure you can do probabilities, but that means you have to have experiments, you have to have some information, and you get into this question about the channel, how many experiments I need to know so I can have realistic probability models. Another one is to use bound, deterministic uncertainty. Is there anything you've done in that?
Oh yeah, that's what
But then you have to set
we use bound all the time. But the problem is that you may end up with a lot of conservatism there because bounds,
But-
bounds can be 0 plus infinity,
but-
and that's what you're gonna see most of the time.
Because
Very large bounds.
said value computations have advanced now to the point where you can do lots of them very fast.
No, but the question, the reason why we looked at this, because the question is really, for what you don't know, it may be good. But for what you know, you better look at the chances that something may go wrong, because otherwise your system is going to be very much over-designed.
Yeah.
It's true that, you can find a probability of 10 to the minus 4 that at the end of the mission you will not be able to land because your fuel is too hot. Is that a risk you can take, or not? If you can evaluate the probability, it will be better, because otherwise you build a system that can fly in any condition, but you will never need it.
And you mentioned about this startup, but let me ask you if I understand correctly. One question that puzzled us for many years, although some of the chemical engineers have been able to do these things, is what's called order of significance analysis. Like I look at the various pieces of the component, their parameters, and I say, for this metric, it's this piece that's very important, and the rest of it we ignore. Okay. Do you have any tools that
Yeah.
try to answer that kind of
Yes. So
Okay,
this
so
AIM-Dyne is one company we work with, and they have this tool which is impressive.
All right.
That's important.
Yes.
More from a cultural aspect. You started this, the motivation for this was that the effort was placed, too much effort, most of the effort was placed in the validation phase and not in the beginning. Now, your methodologies are supporting thinking in the beginning. Is this culture change going to be an accepted culture change within United Technologies? Because that's a significant
Yes.
change to the whole process.
You have no choice.
Very much. But I think at some point, we have seen DARPA running these programs. That will mean that DARPA at some point will require a bit more of kind of rigorous system engineering. Right. Because again, at the end of the day, you do projects for them. So and then if there's let's take the JSF. I don't want to pick on that. On on that aircraft. But the government pays for the cost overruns as well. So there are delays, everybody's waiting, So it's good for the government to have a way of saying, okay, that it will be delivered on time because there is this new methodology that can do it. That's one reason for it. But for the company itself, being able to develop a product fast and with minimal testing, even if it's an air conditioning system, it's very important. So the company is definitely up to this challenge.
Any other questions? Okay, so if you want to continue the discussion, remember we're going to meet back here at 3 o'clock. Right. Let's take this video again.